Autonomous vehicles are one example of a much broader class of systems, autonomous cyber-physical systems. These systems sense the world, reason about it, and act on it in real time. In this setting, security is no longer only about protecting software. It is also about protecting perception, decision-making, and the interfaces that connect sensing to intelligence. In our work, we study this problem through what we call the body-brain interface view. The body includes sensors, actuators, and controllers. The brain includes AI models for perception, planning, and control. And the interface includes the communication and timing infrastructure that connects them. For autonomous driving, that interface is just as important as the sensors themselves. Modern autonomous driving systems do not rely on a single sensor. They rely on multimodal perception. A camera gives rich texture and semantic detail. LiDAR gives accurate geometric depth. When these two modalities are fused correctly, the system gets a much better understanding of the scene than either sensor can provide alone. But this only works under one critical condition: the two streams must describe the same moment in time. If camera and LiDAR are properly aligned, fusion improves perception. If they are not aligned, the system may combine a current camera frame with an older LiDAR point cloud. And when that happens, the model may no longer perceive the present world. It may perceive a distorted mixture of the present and the past. This is not a small calibration issue. Temporal misalignment can directly create unsafe behavior. An object may appear shifted from where it really is. A vehicle may seem farther away than it actually is. A tracked object may suddenly jump, disappear, or be assigned the wrong identity. So before we even talk about attackers, there is already a very important lesson. Multimodal fusion is only trustworthy when temporal alignment is trustworthy. That observation motivates the first part of our story: what happens when an adversary deliberately breaks that timing assumption. Our first work is called DejaVu. The core idea is stealthy, but powerful. The attacker does not need to spoof sensor content. The attacker does not need to change the pixels in the image or the points in the point cloud. Instead, the attacker only manipulates time. That means the data itself can remain valid and benign. But the system is tricked into fusing sensor streams from different physical moments. So the deception is subtle. Nothing looks obviously fake. But the fused perception is no longer faithful to reality. To understand how this attack works, let us follow the perception pipeline step by step. First, camera and LiDAR sensors capture data independently. Each sensor generates its own stream of observations. Second, each message is assigned a timestamp. These timestamps are then used by the fusion node to decide which camera frame should be paired with which LiDAR point cloud. Third, the system performs approximate temporal synchronization. In practice, this often means pairing messages whose timestamps are closest. Under benign conditions, this works well. The reported timestamps are close to the true capture times, and the selected sensor pair is semantically aligned. But under DejaVu, that assumption breaks. An attacker can target the timing infrastructure in several ways: by disrupting clock synchronization, by manipulating timestamp integrity, or by replaying valid messages through middleware such as ROS2 or DDS. Once that happens, the synchronizer still believes it is selecting the correct pair. But in reality, it is pairing sensor data from different moments in time. So the perception model receives inputs that appear consistent in timestamp space, but are inconsistent in the physical world. And that is exactly where the failure begins. Now we can visualize what this means. In the benign case, the predicted boxes line up closely with the ground truth. But under DejaVu, even though the LiDAR data is still valid, it is delayed. As a result, the fused prediction shifts toward where objects used to be, not where they are now. Some objects are displaced. Some are partially missed. Some may become ghost-like artifacts of an earlier scene. This is why temporal misalignment is so dangerous. The system is not hallucinating random noise. It is making confident predictions from stale but plausible data. To show that this is not only a theoretical issue, we built a hardware-in-the-loop testbed. Our testbed emulates an in-vehicle automotive Ethernet environment using multiple Raspberry Pi units, time-sensitive network interface cards, media converters, and a TSN-capable switch. This setup lets us model realistic sensor communication, clock synchronization, and fusion behavior in a controlled environment. We then evaluated DejaVu across multiple models, tasks, and datasets. For 3D object detection, we found that the system is highly sensitive to LiDAR delay. In MVXNet on Kitty, even a one-frame LiDAR delay can cause extremely large degradation, with car detection map dropping by up to 88.5%. For multi-object tracking, the pattern changes. Tracking turns out to be much more sensitive to camera delay than LiDAR delay. In MMFJDT on Kitty, a 3-frame camera delay can reduce car MODA by 73%. To go beyond model-level metrics, we also tested the attack in an end-to-end autonomous driving setup. We used Awesome Lab as the world simulator, AutoAir as the autonomous driving stack, and ROS2 as the middleware connecting the system. In one scenario, delayed LiDAR data makes an oncoming truck appear farther away than it really is. AutoAir decides to proceed, and the result is a direct collision. In another scenario, the truck has already passed, but delayed data makes the system believe the object is still present. The vehicle brakes for a non-existent obstacle, creating a phantom braking event. Once we know that timing is an attack surface, the next question is, how do we defend against it? That gap motivates our second work, AION. AION is a lightweight defense designed to detect temporal misalignment attacks at runtime, without redesigning the whole perception stack. The main idea behind AION is simple. Instead of trusting timestamps alone, we ask whether the camera and LiDAR streams still make sense together over time. AION first maps camera and LiDAR features into a shared representation space. Then it looks at a short temporal window and builds a cross-modal similarity matrix. Under benign operation, corresponding camera and LiDAR observations align well over time, so the strongest similarity follows a diagonal pattern. Under attack, that temporal relationship changes. The best alignment path shifts away from the diagonal. AION uses dynamic time warping, or DTW, to trace that path and convert the deviation into an anomaly score. The first way to understand AION is through the similarity heat map. Under normal conditions, similarity is concentrated around the diagonal, which means the two modalities are evolving together over time. Under temporal misalignment attack, that pattern becomes distorted. The alignment path shifts, spreads, or bends away from the diagonal. This gives a very intuitive visual signal. Benign fusion looks temporally coherent, while attacked fusion does not. The second result is the anomaly score over time. Across attacks such as constant, random, reversal, jitter, burst, drift, and scheduler, AION consistently produces higher anomaly scores during malicious intervals than during benign intervals. That means the detector is not only explaining the attack visually, it is also producing a practical runtime signal that separates normal operation from manipulated temporal behavior. Finally, we evaluate overall detection performance using ROC curves and OROC. Across datasets and fusion backbones, AION achieves strong performance for camera-only attacks, LiDAR-only attacks, and cross-modal attacks. In autonomous systems, time is not just a systems issue. It is a security issue. DejaVu, published at SatML, shows that breaking temporal alignment can disrupt perception. AION, published at ICLR, shows that temporal consistency can be monitored and defended. And together, they point to a broader lesson for trustworthy autonomy. Temporal trust must be treated as a first-class security property. Thanks for watching.